All right. Questions at all about the class, about what we've been learning so far? I know probably top of your mind is the exam. And so any questions about that as well, I'd be happy to answer right now if they're brief. Reminder that we will have office hours immediately after class today. Did you guys see the long email that I wrote early this morning? Everything there kind of makes sense. Any questions at all about how the exam will be administered?
So if we have like PDFs and things on our laptop, we can use those, correct?
Yeah, as long as they're not like, as long as, you know, they're associated with the class. So the class textbook and stuff like that. If you went online and found, you know, ChE421's exam solutions, then please don't use that.
Makes sense. Thanks.
Mm-hmm.
So like the PDF with like the exam questions and everything will be on Canvas. We download it, we have it open on our computer, and then we just like do all the stuff by hand on our.
Yeah. I suggested a printer for you guys just because like I find it easier to not stare at a screen the whole time.
You do, no worries.
Yeah, and like I physically find it easier to have a textbook. During an actual, like if this were in person, I actually would not allow you to bring your laptop, and so you would be, if you had only a PDF version of the textbook, then you would be forced to you know, print out the textbook. Or sometimes or what sometimes happens is I will have like one copy of the textbook in the front of the room, and then people can borrow it if they need during the exam or something. Yeah, I mean, with this situation, it's not really anything you can do about it. Someone say something in the chat. I can just unmute yourself and ask. What did someone? Let me see. Gary said, "Can we use our?" Yes, you can use your phones to scan and it'll work. Yes, I mean, I'm not an idiot. Like let just, you know, do what you can to get this to work under difficult circumstances. We're trying to make it as normal as possible, in that, like, you know, this would be an exam that would happen under normal circumstances, basically, except, you know, obviously we can't all do it together.
Thank you.
Okay. All right, so as I mentioned today, I'm gonna again talk about new material. Also, as I mentioned, that email class is gonna be canceled on Friday, so hopefully, I don't know if the event is supposed to last much longer than, I think it was supposed to go to 2:30 or something like that, but no one's gonna stop you from just hanging out a little bit longer on Lakeville. Hopefully it won't be too cold, I think I'm planning on being there, although I feel a little better today than I did on Monday. On Monday, I felt terrible. But hopefully, if I feel okay and stuff, I'll be around and you guys can complain to me directly about how poorly the exam went the previous night if you wanted to. Okay. But today, new content, right? And so let me make sure I'm sharing. Okay. Can everyone see my screen? Am I ready? Yes. Can anyone see my screen? Am I writing?
We can see your screen. You're just a little bit quieter.
Yeah, I apologize. I'm gonna try and yell, but the difficulty with the microphone and stuff is annoying.
You're fine now.
I'm fine now. Okay, good.
Got better again for a moment. It was like really muted, but now it's fine, I think.
Okay. Well, please yell as soon as you have any sort of sound or visual issues or anything like that. Okay. So today we're going to continue what we've been. Excuse me. Today we're going to continue what we've been talking about when it comes to approximation, except we're going to move on to a slightly different way of approximating. As we were talking about in the past couple lectures, we were talking about a more specific case when we would have a flow geometry where you could approximate it easily as something that's nearly unidirectional, right? And then we used, we were able to do some scaling stuff, show that the Navier-Stokes equation basically follows what we had always been using for unidirectional flow. And then with a slightly different solution method and stuff, but you know, still mathematically similar, you could basically solve the original equation, even though, as we said, there are multiple directions of flow, and you know, VZ or VX or VY could potentially depend on X and Y, for instance. Today we're going to talk about an approximation technique that's a little bit more general. I'll call this perturbation analysis. And to do this, actually, we're going to need to draw upon some stuff that we haven't explicitly taught in the class so far, just because it's a little bit easier to deal with as a mathematical concept. We're going to actually be talking about heat and mass transfer, but I think most of you guys have taken an undergrad heat and mass transfer class. If not, the math should be very similar to what we would learn in a fluids class. Okay, so I'll just say a quick example of reaction and diffusion in a catalyst slab. Okay. All right, let's say we have a slab of material. It has a width of 2h, and so it goes from x equals negative h to x equals h. There's some concentration of some reactant species in the middle of this catalyst slab. That's equal to some concentration as a function of x. We'll say it's reacting at steady state or something. Okay. And there's some concentration of the material, and there's some concentration of the material outside this slab as well that we'll call C0. And what we're going to try and figure out is what is the concentration profile of this reactant inside this slab of catalyst. Okay. Likely at some point in maybe undergrad heat and mass, you guys have solved a problem that looks very similar to this, right? And so hopefully this is not going to look all that different. But the mathematical concepts will potentially be quite interesting to you guys. Okay, so if we assume, for instance, that our species that's given by our concentration is consumed in a first order reaction. So this is the Professor Seitz and Professor Wang crossover lecture, if you will. Then we could think of an ODE to figure out the concentration profile in this catalyst slab, and that ODE might look something like this. Okay, again, we're at steady state, so nothing in time. If you guys don't know where this OD came from, it's not really a big deal. Again, I'm just purely teaching you the math at this point. You'll learn more about the actual underpinnings of this, but just so you know, it's also a mass conservation equation and stuff, and you can derive it very similar to all the time that we spent earlier deriving the conservation equations for fluid mechanics as well earlier in this class. Okay, as we keep mentioning before, you need one boundary condition for every derivative that you have in your equation. That's true in heat and mass transfer as it is in fluid mechanics. That's basically just a mathematical sort of concept. And so we are going to need boundary conditions, and luckily those can be determined pretty easily in this case. It's just that the concentration is equal to C0 at x equals plus or minus h. Okay. To make our lives easier, I'm going to go ahead and non-dimensionalize this equation. Okay, so to do that, I'll have some variable f that I'll call my non-dimensional concentration. So it makes sense to just assign that as C over C0. And then I'll also have my C as a non-dimensional position x over h, like that. Okay. And so then if I plug in these non-dimensional variables into my equation here, then it should be fairly straightforward, right? And so this first term right here, d times d squared c dx squared, is d, here I'll make this a little bigger, is d, and then this d squared c dx squared has 1 unit of concentration up top and 2 units of position on the bottom, so I should get C0 over h squared. And then, of course, my non-dimensional quantity. That. Okay. And then the second term is even easier. That's just concentration, and so it has 1 unit of concentration, so K times C0, and then times my non-dimensional concentration. And of course, it equals 0. And so if I can simplify this a little bit, what I get is d squared f dc squared minus k h squared over d times f equals 0. Okay. And often when we non-dimensionalize, we discover that there are natural groups of different parameters in our problem that tend to be that often are non-dimensional as well. And so in this case, we can let our epsilon be defined as kh squared over d. I honestly don't remember what the actual name for this dimensionless group is. If any of you guys know, just yell it out. Might be something like a Don-Kohler number or something like that. But anyway, we're going to call it epsilon in our problem right here, right? And you know, kind of like a Reynolds number. If the Reynolds number is high, then inertia matters more. If the Reynolds number is low, then viscous matters more, or something like that. In this case, if epsilon is much greater than 1, then that means that reaction is much more important than diffusion. Okay, and of course, if epsilon is much less than 1, then that means that reaction is much less important than diffusion. Okay. Hopefully, none of this is all that surprising to you guys, right? I'll nod your heads if this all sounds halfway familiar from those of you that took undergrad heat and mass transfer. Okay, good. Okay, so now let's go ahead and solve this equation. Okay, this equation with this new definition of epsilon here reduces down to this. Okay, with new boundary conditions that can be defined in terms of our non-dimensional variables, like that. Okay, does anyone know what the solution to this differential equation is going to be? It's a second order linear differential equation, right?
Is it sines or what is it, hypersines and
hyperbolic sines and cosines, right? I think there was a question in office hours about like what do we know the solutions are for these are. For a second order linear differential equation, if there's a plus here, then it's usually sines and cosines. If there's a minus, then you kind of have a choice. You can either use exponentials, which we did when we were talking about Stokes' second problem. Scroll back in those notes if that doesn't sound familiar at all. Or you can also use hyperbolic cosines and sines. And in general, it makes a lot more sense to use exponentials if you're dealing with something that has an infinite domain. So your x values go from 0 to infinity or something like that. Whereas if you're dealing with a finite domain, in this case, where x only goes from -1 to 1, or in this case, c only goes from -1 to 1, then it makes a lot more sense to use hyperbolic cosines and sines. Okay, and the reason is because with exponentials, if you go from 0 to infinity, then one of the exponentials has to decay and one of them blows up, and so that allows you to satisfy with boundary conditions more easily. Okay, and so we can find an exact solution in this case. That exact solution is f equals c1 times sine h plus c2 times cosine h. Okay. And the square root here is just to make it all kind of work out once we plug it into the solution, into the OD, right? And then, you know, just like we normally would, you can figure out what the integration constants are by applying the boundary conditions, right? So let's go ahead and apply the boundary conditions. Okay, so what we get then is if we apply one of the boundary conditions, let's say +1, then we have f is equal to 1, c1 times sine h square root of epsilon, like that, plus c2 times cosine h square root of epsilon. Okay, and then we can also apply the other boundary condition where we note that sine of a negative number is just equal to the negative sign. So we get the sine of negative square root of epsilon is equal to negative sine of square root of epsilon. Okay, that's not true for cosine, and so cosine of negative square root of epsilon is just equal to cosine of square root of epsilon. And you solve these two equations simultaneously for C1 and C2. You get that C1 has to equal 0, and that C2 has to equal 1 over cosine of square root of epsilon. And so what that means then is you have your concentration profile. F of epsilon is equal to okay, and this is the non-dimensional form, of course. You could plug in our definitions up here, epsilon being kh squared over d, and c being x over h, and of course concentration being c over c0. And essentially you have a concentration profile of our species in our slab. Okay, we're only like 10 minutes into the lecture at this point, and we're kind of done here, right? So obviously I'm going to tell you a little bit more about this particular problem. We kind of got really lucky in this problem, if you will, because this problem was formulated in such a way, for instance, first order reaction and pretty simple geometries and stuff like that. It's formulated in such a way that it actually allows us to just solve the problem in basically 10 minutes, right? You know, we got a really simple ordinary differential equation. Adrian was able to tell us immediately that it's sines, that it's hyperbolic sines and cosines. We plugged it in, and then we found the boundary conditions, and then we found the integration constants, and we got the answer. Okay. In a normal condition, that might not be the case. If this problem were even slightly more complicated, then we would be kind of screwed, and our solution here would not work. For instance, let's say we have a second order reaction. If we have a second order reaction, then our OD would be yada 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 minus kc squared, right? And then our ordinary differential equation will have slightly different things, slightly different ways of non-dimensionalizing it, because our k would have different units. You know, you guys know this from Lindsay's class at this point, right? But here would have an f squared, and the solution would almost certainly not be sines and cosine hyperbolics, right? In fact, I don't think there actually is a solution to that you could write down. And so in this more general case, how are we going to solve this problem, right? And this is where approximation comes in. So what I'm going to introduce today is a concept called regular perturbation. I'm going to write this a little bit better. Regular perturbation. Okay. It's basically an approximation when whatever parameter we're dealing with, we'll continue playing with this particular example. Okay. When whatever parameter you're dealing with becomes much, much less than 1. Or is the limit when that parameter is small, basically. Okay, so let's continue with this example. We already know what the solution is, and so that'll make it even easier to evaluate whether our approximation is okay. If that's the case, then again, we'll let epsilon go to 0. In this limit, we can solve this ordinary differential equation, right? For example, if we actually do let epsilon equal 0, then the ODE becomes this. And the boundary conditions become okay. Does anyone know what the solution to this differential equation is? So again, this is what the ODE is once we let epsilon equal 0, right? Does anyone know what the solution to this differential equation is?
Would it just be a linear function?
It would just be 1, actually. Right. Yeah, it will be a linear. It will be a linear function. Yes, you're right. But I'm skipping several steps ahead. It's a linear function that has to go through the point 1, 1 and negative 1, 1, and so it's just going to be 1. Right. So the solution is just so that's even simpler, right? But that doesn't actually tell us anything physical about what happens when epsilon is something small, right? I'll say that this makes sense if epsilon actually equals 0. We have no reaction. Right? Because the way that we drew this problem up here is we have a catalyst slab right here, right? That consumes our reactant and reacts it into something else. Okay, and so if we have no reaction, then it totally makes sense that because the boundary conditions are C0, then throughout the entire catalyst slab, you should expect the concentration of that reactant is going to be C0, right? You would expect that if there is some reaction, then the concentration will be depleted somewhere in the middle of this catalyst slab. And the game is going to be what is the concentration actually going to be, and how is it going to be a function of x, right? But in the most boring case possible, if there's no reaction when epsilon actually equals 0, then you should get exactly what you expect, where there is just no concentration gradient and the concentration is equal to C0 everywhere. Make sense? Okay. Now I'm going to ask a slightly harder question. What if epsilon is small, but non-zero? Okay, and here's where the regular perturbation analysis comes in. Okay, we're going to do something kind of like a Taylor expansion, which, again, all of you guys have seen before. But we're going to do it in kind of a weird way. We're going to say that our solution f as a function of epsilon, or I guess our solution f as a function of c, can be written kind of like a Taylor expansion. Okay. It can be written like this. Okay. Now f is a function of c, or x, or whatever, okay? And so therefore, all of these individual terms here, f0, f1, f2, f3, et cetera, are also all functions of c. And so if we knew somehow what the values of, or what those functions actually are, f0, f1, f2, et cetera, then you could completely determine what our solution f is. And you could evaluate as many of these terms as you want to get to as close an approximation as you want to your actual solution. And this whole thing totally works if epsilon is small or close to 0 here. Because then if epsilon is close to 0, then you would only have to evaluate a few terms, because as you go farther and farther and farther along the sum, then the terms become smaller and smaller, and so you don't really care about them anymore. Does that kind of make sense? So the game is going to be to actually figure out what these functions f0, f1, f2, and f3 and such actually are. Okay. And the way we're going to do that is we're going to take this function and actually plug it into our ODE. And that will actually help us solve for what f0, f1, f2, and f3 and stuff like that are. Okay. And what you'll find is that it's actually not necessary to solve for all of them. You actually only need to solve for the first couple, and then that actually gives us a pretty good approximation in this limit where epsilon is small. Okay, so here we go. We're going to plug this into our ODE. Okay, just to remind you guys, the ODE looks like this, right? And so we're going to take a derivative or two derivatives with respect to c right here for this first term. So the first term is going to look something like this. Okay. And that second term is just epsilon times f, right? And so let me just go ahead and plug it in. I have epsilon times f. Sorry. Zero. And what I'm going to do now is I'm going to multiply this product out, and I'm going to group together the terms that have the same power of epsilon. Okay, and so what I get then is that like that, right? Because I have an epsilon d squared f1 dc squared, that's where this term comes in. And then here I have the term that has 1 power of epsilon is just f0 right here, right? That I get an epsilon f0, and that's where this comes in. This over here, similar idea, right? This first term comes about because of this term right here, and this term is because of this. When I multiply here, I get a negative epsilon squared times f1, right? This all kind of makes sense. And now this whole equation, or this whole different equation stuff has to be true regardless of whatever value epsilon I happen to have, right? And so the only way that this equation can be equal to 0 at any arbitrary value of epsilon is if all of these individual terms are actually equal to 0, right? And that condition where all these individual terms have to equal 0 then allows me to find equations that determine f0, f1, f2, f3, etc. So let me just write that out in words. Each term must be 0, epsilon. So if the equation is true for arbitrary epsilon. Okay. And so then we can evaluate the equations to get a better and better approximation to our solution. Okay. Here's what I mean when I say that. I'll do a little bit of a shorthand. This gives us basically an infinite number of equations that we can then evaluate, right? I'm going to call the first equation the big O of epsilon to the 0 equation. That's this first equation, or that's this first term right here. That has to equal 0, right? That implies that d squared f0 dc squared has to equal 0. Okay. I will also have an epsilon to the first term. That's this equation right here, right? Okay. And I'll also have an epsilon squared term. Like that. And et cetera, et cetera, et cetera. Right? And maybe you guys now can see how this technique is powerful. Because perhaps we can figure out a simple solution right here. We actually did that already earlier, right? This is the case where we have no reaction, where f0 is just equal to 1. We just did that up here. Okay. But then once we have f0, then we can, that's the same f0 as over here. So we can just plug that solution in over here and then use that to calculate what f1 is going to be. And this is an even easier differential equation to solve than the one that we solved earlier where we got the hyperbolic cosines and sines, right? And then once we get f1, then we can use f1 to solve this differential equation for f2. And then we can do this until our little hearts are content, right? And luckily, because it's a regular perturbation expansion, In other words, where epsilon is small, you don't actually need that many terms here before you can get a pretty decent approximation to what your answer is going to be. Does that kind of make sense? Nod your heads if you agree, shake your heads if something doesn't really make a lot of sense.
And
The one thing that I have not talked about yet is all of these are individual ODEs. They all need individual boundary conditions, right? So let me show you guys how to get the boundary conditions, unless there was a question. Sorry, I saw someone unmute themselves, I think.
that was my question.
That was your question. Okay, cool. So we're gonna need the boundary conditions, right? So let's deal with the boundary conditions. Okay, the boundary conditions. Normally what the boundary conditions say is that at C equals plus or minus 1, okay, then F is equal to plus or minus 1. Excuse me. What that implies then, sorry, not F is equal to plus or minus 1, F is equal to 1. I don't know why I said that. F is equal to 1, okay? What that implies then is that 1 is equal to F0 plus epsilon F1 plus epsilon squared F2 plus etc. Right? And so just like before, we can group together the terms for epsilon to the power of 0, epsilon to the power of 1, epsilon to the power of 2, etc., etc., etc. Right? So for instance, I could bring this over to the right-hand side and say it's equal to 0, and then I can group together the ones that have multiple of epsilon to the 0 power. That will tell me then that at C equals plus or minus 1, I must have F0 equals 1, F1 equals 0, F2 equals 0, etc. F3 is also equal to 0, F4 is also going to be equal to 0, etc., etc. Okay, and that's just because, you know, there's no term on this side where epsilon is equal to for a epsilon to the first power. There's no term for epsilon to the second power, etc., etc. And so therefore those are all equal to 0 as well. Okay. And so again, the game is going to be to actually figure out what F0, F1, F2, F3, those are all functions of C. And so we need to solve ordinary differential equations and boundary conditions to figure out what those functions actually are going to be. Okay, so let's go ahead and do that. We already did this problem for F0, right? That's right here. When epsilon goes to 0, or in this case, you know, same ODE right here, right? This ODE is exactly the same as this ODE. This boundary condition that F has to equal 1 at C equals plus or minus 1 is exactly the same as this boundary condition. And so therefore, F0 is equal to 1. Okay. So I'll say the solution to the order 0 problem I'll say order 0 solution. That's just F0 equals 1, say from before. Okay. And so let's look at maybe the more interesting problem. Okay. In this problem, then basically we need to solve this differential equation for F1. Okay, this is the order 1 ODE, right? So let's go ahead and do that. We have d squared F1 dc squared is equal to F0. Okay. And we found from the order of epsilon to the 0 solution that F0 is just equal to 1. Okay. And of course, we need 2 boundary conditions, but we found those boundary conditions already. That's this right here, right? At C equals plus or minus 1, F1 is equal to 0. Okay. And so then we can basically solve this differential equation. This is actually a really easy differential equation to solve, right? Does anyone know what the solution to this differential equation is? D squared F1 is equal to 1.
Like it's a quadratic, but
It's a quadratic, right? If you couldn't see that immediately, that's okay. Just integrate it twice and you'll see it, right? Integral of a constant is a linear, integral of that is a quadratic, right? And so F1 of C is equal to 1/2 C squared plus C1 C plus C2, right? And then again, we'll apply the boundary conditions. So what we get is that at one of the boundaries, let's say xc equals +1, we get 0 is equal to 1/2 plus C1 plus C2. At the other one, we get 0 is equal to 1/2 minus C1 plus C2. Solve these two equations simultaneously, and you get immediately that C1 is equal to 0 and C2 is equal to minus 1/2. Okay, and so you get that F1 of C is equal to, I'll write it like this, minus 1/2 1 minus C squared, like that, okay? And so if all we cared about was just the order of epsilon to the 1 solution, then we can just write our overall solution is F0 plus, or in this case, it's minus because the answer is negative, minus the order 1 solution. And then, of course, we could keep going to figure out what our order 2 solution is going to be. Okay. And basically, we can just continue as far as we want, right? We can continue indefinitely. Okay. Does this kind of remind you guys of a Taylor expansion? Sort of? It's kind of like a Taylor expansion, except it's like we're pre-assuming that our solution is a Taylor expansion, right? In a Taylor expansion, what you would actually do, and one of the homework problems will ask you to do this, is you would take a known solution, or you would take a known function, and then you would expand it in terms of, let's say, epsilon, right? And in general, to do a Taylor expansion around epsilon equals 0, for instance, you would take a first derivative of f, evaluate it at epsilon equal to 0, and then that would be the answer would then be like f of epsilon f of 0 plus df d epsilon times epsilon to the first plus d squared d epsilon squared epsilon times epsilon squared, et cetera, right? That's how you would do a Taylor expansion of an arbitrary function. In this case, we don't actually know what the Taylor expansion of f is going to be because we don't actually have the solution of f. Okay, I'm cheating. In this case, we do. But pretend like we didn't know that. If we didn't know that, we can basically assume that our final solution has some sort of Taylor expansion form and then figure out what those actual terms are, right? And in the homework, what we will actually ask you to do is you could, for instance, in this case, because you know what the solution actually is, you could evaluate a Taylor expansion of this using epsilon, expanding out in terms of epsilon, right? That should match exactly, mathematically it has to be true, right? That should match exactly to the solution that you get from your regular perturbation analysis. Make sense? Okay, just for good measure, we can continue indefinitely. I'll say here, can verify with Taylor expansion, okay? around epsilon equals 0. Okay. Just for good measure, and because we have maybe like 10 minutes left or something, I'm just going to go ahead and do the next problem as well. That's the order of epsilon squared solution. But it gets repetitive. It gets pretty repetitive after that. Okay. In this case, maybe it's slightly more interesting because our F1 solution was maybe a little bit more interesting as well. But again, here was our ODE in the epsilon to the 2 case, right? Looks pretty similar to our ODE in the epsilon to the first case, right? So let me just rewrite that down here. And again, we know what F1 is. Our F1 is just given right here because we solved for it last time. Like that. And we also have boundary conditions here. That was that 0 boundary condition thing that we got by expanding the original boundary conditions out, right? And so now we need to solve this differential equation. You guys might not see this differential, the solution to this off the top of your head. That's totally fine. I don't either. But it's a really easy differential equation to solve, right? It's just you have to integrate this twice and then you get the answer, right? And so let me go ahead and do that. Integrate it once. So if I do that, I get this. And integrate it again. And I get this. And I like to, make everything look nice and tidy and everything. And so I'll make it look like this. Okay, just like before, I can apply the boundary conditions, right? So I'll go ahead and do that. Okay, at CE equals 1. Then I get 0 has to equal, so I'm going to plug in x equals 1 here. Here I get 1 minus 6, so minus 5 over 24 plus C1, plus C1 plus C2. And then, of course, x equals -1. I get, again, 0. Here again, I get minus 5 over 24. Here I get a negative C1 because there's a C right here, plus C2. Solving simultaneously, again, I get C1 is equal to 0 and C2 is equal to 5 over 24. Okay, and so then in this case, what I get is the solution for F2 is just, I'll make it look nice and tidy again. Is that. Okay. Excuse me. And so then the overall solution that now includes order of epsilon squared terms in it is F0 plus F1 times epsilon. This right here is my F1, right? Plus F2 times epsilon. And again, we can keep going as far as we want to our little heart's delight. Okay, I'm going to try and quickly verify that what I did here is not a lie. Okay, so give me a second to grab my keyboard. All right, so Here's MATLAB. So the actual solution is this, right? And so let's give myself a value of epsilon. Let's say epsilon is, let's say something small, 0.1, like that, okay? And I need some x values from -1 to 1, like that, okay? And so let me go ahead and plot x times cosine of square root of epsilon times x. Yeah, where's my plot? There it is. All right, cool. Okay. This is sort of what we would expect, right? Am I doing this right? I did not do this right. I forgot an H right here. Okay, this is sort of what we would expect, right? The concentration at the two ends is equal to 1. And then, as we mentioned, the catalyst depletes the concentration of the reactant somewhere closer to the slab, right? Notice the y-axis here only goes to 0.95 because there's not that much of a reaction because our epsilon is small. It's only equal to 0.1, right? And now if we wanted to plot some stuff, we wanted to plot our actual solution, perhaps I can show you guys that this solution actually gets closer and closer to our expected solution here. Okay, so let me pull up the MATLAB command window, and then here's my actual figure here. Okay, so if I were to plot just 1 right here, would even let me do that? Okay, I think there's a line right here. You know what? I'll change the axes here so it's a little bit easier for everyone to see. Excuse me. Oh, okay. I don't think it'll even allow me to plot 1. Okay, sorry, I can't plot 1. You guys know what 1 looks like. It's just a horizontal line, right? If I were to plot the next one right here, hope that's right. It's actually a decent approximation, right? And you know, this is a way simpler solution to deal with than having to remember what cosines and sines are hyperbolically and stuff, right? But you know what? I could go even farther. Let's make this one green. Sound good? And so the next one's going to be, let's see, c to the 4th minus 6 times c squared plus 5 times epsilon squared over 24. Okay, maybe you guys don't believe me, but there's a green line like literally right on top of the blue line right here. Okay, I can zoom in if you don't believe me, but it's there, I promise. That's because the solution's actually really, really good. You can maybe see the green line here as well, right? And so you can see like the solution actually turns out to be pretty good, right? And again, if you wanted to, you could take the original solution and do a Taylor expansion around epsilon, and you should basically arrive at this. Okay. You can do this for other values of epsilon as well. So again, this is a great approximation if epsilon is small, because of the way that the perturbation expansion is engineered, right? The smaller the epsilon is, then the fewer terms you're going to need over here, because those terms become even smaller later on. For instance, if I had epsilon of only 0.01, then I could plot my original thing right here. Okay, that's what that looks like. Notice how the values here are even closer to 1 at this point, right? But here, I could plot my first order solution. And the first order solution is essentially an exact approximation, right? Now I'm not even going to bother plotting the second order solution, but it essentially looks identical to it. It's the approximation is like almost exact at this point. If my epsilon's not great, let's say my epsilon is 1. I think when we do 1, it's actually not terrible. So let's give ourselves another figure. Here's a solution of epsilon's equal to 1. Like that. Okay. Now if I try and plot my first order solution, it's not so great anymore, right? And that's just because, well, when epsilon is, in this case, actually it works even when epsilon is, or it's actually not terrible when epsilon is equal to 1. But in general, one approximation for all these that epsilon must be much less than 1, because that way our sum here will eventually converge, right? We could do our second order solution as well. There's a second order solution. So maybe a little bit better of an approximation, but definitely not so great at all anymore, right? And of course, when we're dealing with what happens when, let's say, epsilon is really large, the other limit when epsilon is much greater than 1, right? Maybe you guys can visualize physically what's going on when epsilon is really large. When epsilon is really large, reaction becomes much more important than diffusion, right? In that regime, what you might expect is something like this, where maybe all of the reactant is completely consumed in the middle of the reactant slab, right? Later on, maybe on Monday or something like that, we're going to deal with the cases that happen when epsilon gets really large. In that case, yeah, actually, we've completely consumed the reaction all the way in the middle, right? And you can imagine in this case, our perturbation analysis is going to be terrible, right? Let me just go ahead and plot the first order solution. That's terrible, right? That's just because our perturbation analysis is only supposed to work when epsilon's really small. In the limit when epsilon becomes really large, there's another type of perturbation analysis that we can use to still get a decent approximation. Okay, and I'll get to that probably in the next lecture. Okay. Any questions at all about perturbation? Anything of that nature at all? Okay, I'm going to take like a 5-minute break or something like that. If you want to stay for office hours, please do so. Okay. Otherwise, new lecture content on Monday. Hope to see several of you guys at the thing on Friday. And good luck on the exam if I don't see you at office hours or something before then.
Will the office hours be recorded?
Do you want me to record them?
Yeah, and if no one else has an issue with that.
Sure. Yeah, I'm fine with that. I'm going to stop recording right now, and then remind me to start recording once the office hours start again. Okay. If I can figure out how to stop recording, there we go.